Okay, so today we'll have another shorter lecture. We'll finish around 3:30, 3:40. And what we are going to do today is basically introduce angular momentum. Before introducing angular momentum, we'll rewrite the Schrödinger equation for a central potential and see how angular momentum arises there in a natural way. So at the end of the previous lecture, we wrote down the Hamiltonian. Okay, so we said also a couple of words that we'll do here, separation of variables. And the logic is very clear. Look.
Shouldn't there be a multiplication?
So, this term has no dependence neither on theta nor on phi. Once I multiply, the sinus theta falls off. In these guys, at least in the kernel of stuff, again, theta phi, no r, r, no phi. So, makes sense to do here separation of variables. So let's write down the two parts of the separation. Okay, so I write the theta and phi dependent part. Now, this is a constant. You will see that L has to be an integer, but at this point it's just a constant that I write in a funny way. And just can substitute what's written here and put it here and get the second part, the equation on R. Okay, standard separation of variables. Nothing more, nothing less. Okay. Before leaving the part that is R dependent and concentrating on theta and phi, I would like to do some massaging to what's written here in order to bring it to a more familiar form. I can just write it down as some effective potential. Why not? It depends on R. Everything is fine here. And just to shorten what's written here in this form. So that's no big deal. And the second thing I would like to do is substitute R with U in the following way. Again, I'm allowed to do it. So if I'm just rewriting this part, erase it so it won't disturb. So I just substituted large R with U over R. What does that help me in life? Okay, I'll write down here. Well, this is trivial, this is trivial. Let's write down this part. Okay, so I just rewritten this part, nothing beyond that. Okay. just performing the derivative.
Should we just minus here?
Okay, put it in. Fine. Second derivative. So instead of this frightening part, you can just write r times second derivative. It'll give you a couple of seconds to copy it. Okay, we're good. No response. Assume it's good. So I'm just copying what's written here. I had here a power of r. Let's write it this way. And this is a regular one-dimensional Schrödinger equation. We have a kinetic part and a potential part. The potential is a bit strange because we have to write this whole dependence. And there is an additional difference that it's only for r larger than 0. It's only on half the field or the space because by definition r must be larger than 0. But except for these 2 points, we'll have to go back and solve it and we'll get you some solution for u. So we'll set aside this part, the r dependence, which is particular to the form of v, and go and treat the y dependence. So there are two different approaches to continue. One is brute force. I have a differential equation, theta and phi. You can try to solve it. It won't surprise you too much that it will have two stages, separating the theta and phi, and solving the phi, which is actually easy. And then we move to theta, which is a bit more complicated, and we have a solution. That's, well, how someone who's trained only in mathematics would have approached it. We will go through a different route. We will try to understand the physics. And the physics, it goes back to the definition of what is angular momentum. So we'll do a detour and remind ourselves what is angular momentum. Which is, if you have forgotten, usually the symbol is L. R cross P. Great. What do we do in quantum mechanics? We change it into an operator. Extremely difficult. Now it's in an operator form. Why is it so easy? Because R and P we have defined already. So it's just simple algebra to rewrite it in operator form. So R is R, and P is and then either writing down the determinant here. Well, let's write down the determinant x, y, z, x, y, z. I just wrote down the definition, which gives me by definition. assuming that I didn't screw up the pluses and minuses. Okay, so we know each one of the parts, and for reasons that we'll see in a bit, I want to write out also L square. Again, by definition. Okay. I'll put this one down here. So I have some space. Can write it down also in polar coordinates, in spherical coordinates. So. How did I get it? Just from writing the definitions. Now, we have a very cute connection, short and sweet. We have extremely ugly representations, which I already tell you that if during a solution you are forced to write this down, at least if I gave you the question, you did something wrong. No one wants to deal with it. And in a moment I'll say something about this. Why am I so sure that you can work only with this and you don't need these two? Please.
Only with the LZ?
Yeah.
Well, let's say that R is like that, and then you make like maybe let's say conserved angular motion, and then P is always vertical, I think, to R, and then you get only Z.
you complicate the answer too much. The reason is very simple. My potential and the kinetic place is isotropic, doesn't care about theta and phi. So deciding on Lx, Ly, and Lz is my decision, definition of a basis. So choose a base wisely. So you need only Lz. There's no reason that you'll need, because all three components, I didn't say they're equal, but they're the same from point of view of symmetry. So whatever part I want to know, whatever direction I want to know, define it along the z direction. Okay. Now, I'm missing parenthesis. Okay, and
the argument of sinus is d over d theta. Yes.
I think so, because the most is the second power. You have here one outside. Structure is unpleasant, but the most that you can get is the second derivatives. It can't be here a higher power.
So if you define z aligned with that direction, then you have a rotating system, coordinate system?
We'll see at a specific how to pull out, if I know z, how to pull out x and y.
Okay.
The real answer is I can't pull it out because it's non-commutative, but wait a moment. You always can know L square and Lz, but you never can know the other two components because they're non-commutative.
Yeah.
So if you need to know, you can know only one component, choose your basis to be the one component that you can know.
Okay.
Okay. So why did I say that we can always know L squared? Look, I have to do a commutation between Lz and L squared. Right? All these are theta dependence and this is phi dependence. So commutation is 0. Here, it's just a derivative in phi. Again, the commutation doesn't. Is 0. So if I find a basis of Lz, I find a basis of L square and vice versa. Because they commute. Can choose the same basis. Another thing, going back to the Schrödinger equation, the term that was theta dependent was this term. Right? We had all this term divided by 2mr. Which, if you remember anything out of analytic mechanics, this is the term of the energy that depends on the angular momentum. So once I crack up the eigenfunctions and eigenvalues of Lz and L squared, They are the same eigenfunctions, but not necessarily the same eigenvalues. I've solved this part of the solution to the Schrödinger equation.
How did you know that the theta part and the phi part commute?
Two variables always commute if they're different. What was the problem with x and p? P was defined also in terms of x, dou to dou x. That made life miserable. On the other hand, if I have, let's say, x and py, life's good, because dou to dou y and x always commute, because the order there is not important, because the derivative according to y of x doesn't depend. A derivative of theta according to phi doesn't depend. It's just a constant from its point of view.
And so for the other term, okay.
The other term is just the same.
Okay.
So, after seeing this, okay, because H, what does it have? This part, which commutes with L squared, and some part that depends only on R. Yeah, no problem. The part that depends on R commutes with LZ, and LZ commutes with L squared. So the commutation there is 0. Now, the thing that drives us crazy in our classical intuition what is Lx commutation relation with H? Okay, you could be a mathematician and hit your head against the wall for half an hour and get the result. Or you couldn't be a physicist and Lx is equivalent to Ly, equivalent to Lz. It's just a definition of a basis. Lx is a physical operator. It represents something I measure. If I commute with Lz, I commute with Lx. Because it commutes with each part of it. And now comes the mind twisting part. X and Y, X and Z, Z and Y don't compute with each other. Why is that? First, just look on the definitions. You have there in the definitions of Lx, Ly, Lz, multiplications of y times dot to dou x and so on and so forth. So you can go and solve it immediately. It's much easier to prove these things in the Cartesian representations than in the spherical coordinates. Then it goes back to our basically commutation of x and dou x. Let's write down one example and are you familiar with this notation? This is just plus minus according to the permutation. So So I'm just copying the definitions. Okay, I just wrote down the definitions. So, Okay. Two terms I don't have anything to do. The derivatives are according to y, and this is x and z. Can't be a commutation different than 0. Here, again, it's y and the derivatives are z and x. I don't care about it. Here, I have to be careful, and I have to perform it directly, because what's written here okay, and here I have to also be careful. Okay, I just wrote the definition. Okay, so I'm copying this guy. X, y, dot squared, z, the y. And here I once performed the derivative on y, so it's minus x. Z, and the second time.
That should be z times dou over dou x.
So here I did
No, just dou x, not just replace y with
y with 6, right? So again, combine these two up to IH bar, it's just LZ. So the commutation relation between x and z is Ly times IH bar. Unless I did a mistake with some numbers. Same goes for any permutation. XZ, you'll get your Ly. YZ, you'll get your LX. So that's just the proof of what's written here. I have to do it 3 times. I did it 1 time, but the principle is clear. Okay, so what happens here? And in some sense, it's counterintuitive, at least counter-classical intuitive. I know L square. I can know one of the components of L. I'll call it Lz, but I don't know what is Lx and Ly. So I can perform a measurement of L square, the absolute value of the angular momentum. I can perform a measurement of one of its components, but if I measure one of its components, I don't know the other 2. Another example of the uncertainty principle. Okay, so this classical picture, I know L square and I know all components, doesn't exist in quantum mechanics. You can know L square, you can know one of the components, but not all of them. Okay, so armed with these general principles, I have to go and find the eigenvalues and eigenfunctions of these operators, because once I know them, I know part of the solution to the Schrödinger equation. Okay, so what have I written here? Well, I'm using the previous definition of y in the separation of variables of theta and phi, and I'm claiming that it will depend on 2 quantum numbers, L and M. I haven't yet proven what they are, what are their properties, nothing about this. Okay, so L and M, just by counting the number of equations that I have here for L square and Lz, I decide I'll have 2 quantum numbers. I don't know yet what is the exact ways that they depend here. why did I add here h bar? Well, this is a constant. Why did I write here h bar and h bar square? Just from units. Because I didn't define what is this and what is this. It's at the moment any constant. But one of these things we would easily be able to solve. And this is this guy.
Explain again what is exactly your claim here? That the operator...
Delete this and put your constant, and don't say anything on the quantum numbers, L and M. Okay, so this is just an eigenvalue and eigenvector equation, right?
Oh.
Sorry, I've...
Yeah, okay, now. Okay, now.
Okay, so this is the claim. This is an eigenvector and eigenvalue equation, and the notations of M, L I'm writing already now because I know what is the solution and it's easier to see this way. But in general, I should have written here a constant, and I don't say anything about the dependence on L and M. Okay.
Just making sure you want to find the eigen vectors, because then you can find the eigenvectors of the Hamiltonian.
Yep. If I know the eigenvectors of Lz and L square, I know the eigenvector, the part that depends on theta and phi of the eigenvectors of the Hamiltonian.
But you only need one of them, right?
I'll need both of them.
But they commute.
Yes, but they have...
Okay.
Lz doesn't come in directly into the Hamiltonian, right?
Yeah.
This guy comes directly into the Hamiltonian because Hamiltonian has an L square dependence and not an Lz.
Right.
Now, if you'll tune back to what you learned in modern physics about the properties of the hydrogen atom, what do you know there? That
N squared times H plus.
you don't have a dependence there in energy, not on M and not on L. Right?
Yeah.
Okay, we'll build it by parts. On M, you couldn't have a dependence because it doesn't depend directly on Lz. We will try to understand why it doesn't depend also on L.
Okay. So for now, we just got, okay.
For now, it's just general linear algebra, or I just wrote it down explicitly. Just wrote the definition of Lz and wrote down the eigenvector equation and eigenvalue equation. Does this equation depend on theta? No. No. So I can can ask why do I add here a dependence on M? Because it's necessary. We'll see. Okay, so the whole dependence on the function of large theta will fall off this equation. Okay, this fulfills the equation. And since I have periodic boundary conditions, each time I go 2 pi on phi, I have to return to the same wave function. Okay, so M is an integer, and the eigenvalues of components of the angular momentum are M times h bar. The good old guess of Bohr when he started the quantization of hydrogen atom. Again, we can go and brute force solve this equation. But like for the harmonic oscillator, I want to now define a new set of operators that will make my life easier and actually show me what is the physics behind these properties.
Second equation?
Yeah, I don't want to go and brute force run into it. I want to define, as I defined A and A dagger, I'll define here 2 operators that will help me get to the solution in a much faster way, or at least define what are the eigenvalues. The eigenvalues. I don't speak. You remember that we could, for a harmonic oscillator, we could know the eigenvalues without really knowing the eigenvectors.
Yeah.
The eigenvectors were complicated, the Hermits. Here they will be the general Legendre. A bit more complicated. But we'll get the possible eigenvalues without going into these more complicated behaviors, eigenfunctions. So I'll define two operators, L plus and L minus. I wrap it up in the same line. They are not Hermitian for the simple reason that if I take L plus dagger, I get L minus, just because of this I. Lx and Ly are of course Hermitian. And let's see what are the commutation properties of these operators. Just wrote down the definition. But I know to perform the commutation with Lx, and I know to perform the commutation with Lz, with Ly, so I know how to write it down. So commutation with L plus of Lz gives me L minus, and commutation with L minus gives me minus L plus. Don't believe me? Check. Straightforward because we defined already these commutation relations. L plus times L minus. What would be the equivalent of L plus times L minus in the language of the harmonic oscillator?
N.
N, exactly. Why? Again, these two are non-Hermitian, but multiplication of them will be Hermitian. So let's draw it down explicitly. Remember, Lx and Ly don't commute, so I don't lose this term. Why is that? Because of the commutation relation between Lx and Ly gives us Lz up to an I times h bar. I have an I here, so I'm left only with the h bar. Because it doesn't look too pleasant, but why? Because L square, as we have written, is Lx squared plus Ly squared plus Lz squared. And after all this exercise, what do I learn? That L plus times L minus has the same eigenvectors as L square or Lz because it commutes with them. Somewhat similar to the fact that n has the same eigenvectors as h in the harmonic oscillator. Same exercise up to a minus here. So we get, instead of plus h bar, minus h bar. And last thing I want to do about those L pluses and L minuses before getting to the solution. Commutation between L plus and L minus is 2h bar Lz. Again, intuitively, completely makes sense because LA, or you have your commutations between Lx and Ly that we know is IH bar Lz. So the I falls off from the definitions of I times Ly, and we have just twice h bar Lz. Okay, so we prepared the ground. And from this, some trivial game with operators, in 5 minutes we'll have a very interesting conclusion. just a different notation. Instead of writing YLM, I'm writing it as in the Dirac representation LM. Okay, but I know exactly what is this thing. It's something composed of L square, LZ square, and LZ. From the definitions that we gave in the connection between L plus and L minus and L square and LZ. I write down a matrix element. I'm allowed to. Right, I move it from here to here, and it becomes, instead of L plus, L minus. So what does it give me? So this basically is a norm of a vector L minus Ln. What do I know about a norm of a vector? Norm of any number, it's positive or zero, it can't be negative. Or why? Because this is the direct calculation of this matrix element. Can play the same game. Again, it's some norm of this time L plus Lm. means that it's positive, or
How did you notice that it acts like a norm?
I just took the definition, let's say here,
Okay.
and I'm always allowed, instead of operating L plus after I operated L minus, to operate it on the Hermitian conjugate eigenvector.
Yeah.
So then it's L minus because it's not a Hermitian. And then I have the same.
Oh, okay.
I have the same vector, and that's a norm. That's a definition of a norm. Same thing in the opposite case. From these two simple considerations, I'm getting a very interesting conclusion. From the first one, L times L plus 1 has to be larger than m squared minus n. And from the second,
Okay, that's it. Do you know that LM are normalized? When you-
no. So I didn't say it's equal to 1.
Oh, okay.
I never claimed that it's equal to 1. The answer is no, it's not normalized.
So you might have divided by a constant, non-zero product.
And if their norm is 0, I still
Yeah.
wrote down this possibility. But what did I conclude from it? The absolute value of m must be smaller than L. Now you remember modern physics hydrogen atom. You define L, and m goes from plus to minus L at jumps of 1, which we haven't yet shown, but this is the root of it. Just because of the algebraic structure of the angular momentum. Very, if you want a very, very simple proof of it. If m is larger than minus L or L, one of these inequalities is not fulfilled. So it's not a norm of a vector, something is wrong. So the only way to fulfill the conditions on the norm is that L is larger or equal to m. You can't choose any m you want, depends on L. Okay, we know that m is integer. We'll do something in the next lecture which will show us actually that not only m is an integer, L is an integer. I'll tell you in secret, or half integer. Okay, so we see that a lot of the structure of the hydrogen atom is not unique to the hydrogen atom. It just comes from the fact that we're dealing here with a central potential. So the degeneracy and everything that you have learned, property of angular momentum, not on something else. What we are going to do in the next lecture, we'll see why L is actually an integer and not anything. And we will see how to add angular momentums. First time that we'll see many particles here. We'll have more than one particle. Why is that so important? Think about elementary particles. We have a neutron or a proton built out of 3 quarks. Each one is a spin half particle. Nevertheless, the neutron and the proton are spin half particles. How does that work? Has to do with the peculiarities of angular momentum. Oh, you could stop me and say, just a moment. This is angular momentum. This is spin. Why do you connect them? They have the same algebraic construct. Okay, another thing that I'll do in the next lecture, because it's a couple of days before the general memorial for the Holocaust, all quantum mechanics was developed prior and during the Second World War, during the Holocaust, and it has a lot of relevance to the emergence of the Nazi movement. I don't know how many of you know that the Nazi movement was perhaps the only political, well, almost only the only political movement that had strong opinions on questions regarding to physics. Was ruled by rules that relativity is Jewish physics and therefore is wrong and can't be taught in universities. And also they had a whole issue with quantum mechanics that unfortunately some of its developers, mainly Heisenberg, was certainly not Jewish. But to solve this problem in definitions, they came out with an interesting and new definition of a Weißjude, a white Jew, which is an Aryan by birth, but somehow he was corrupted to think like a Jew. And that's another definition of racial hygiene and so on. And we'll see how all this had to do with the development of physics and some background on some interesting characters took part in the development. So part of the next lecture will be also devoted to this general topic. Okay, so we'll stop here.
תודה.